Whenever we talk about the actual price tag of artificial intelligence, the conversation almost always drifts to training.
Hmm.
We picture these massive server farms, right? Just burning through millions of dollars of electricity, running for months on end just to teach a model how to speak. And don't get me wrong, that is an astronomical
Yeah,
cost.
oh, absolutely.
Yeah.
It is. But it's really a capital expenditure. It's essentially a one-time cost to build the factory, if you want to look at it that way.
Exactly. And that's actually what I want to dig into today for this deep dive, because once the factory is built, once the model is trained, it doesn't just sit there.
Right.
It has to work. It has to answer questions for you and me. And looking at the stack of research we have for today, the cost of serving these models is arguably the bigger financial black hole.
It really is the silent killer for companies trying to scale this technology. I mean, you can spend $100 million training a model, but if you can't afford to run it for 1 million active users, you just don't have business.
Yeah, and I was reading through this paper from a team of researchers at UC Berkeley, Stanford, and UC San Diego. And they dropped this stat right at the beginning that honestly made me do a double take.
The keyword search comparison.
Yes. They said processing a request for a large language model can be up to 10 times more expensive than a traditional keyword search. 10 times.
And honestly, depending on the complexity of the query, that might even be a conservative estimate.
So our mission for this deep dive is to figure out why. Why is it so ridiculously expensive? And more importantly, how did this team look back at a computer science concept from the 1960s, something literally from the days of room-sized mainframes, to fix a bottleneck in the most cutting-edge AI technology we have right now?
It's such a great story because it isn't about inventing some brand new neural network architecture. It's not about making it quote-unquote smarter AI.
Right.
It's about plumbing. It's fundamentally about how we manage the memory inside the chips.
Exactly. So the paper introduces a system called vLLM and a technique called PagedAttention. But before we get to their solution, we really have to understand the problem. And the researchers identify a very specific villain here, something called the KV cache.
Right, the KV cache.
Now, for the listener who knows their way around a GPU but maybe hasn't dug into the actual architecture of a transformer, let's break this down simply. What exactly is the KV cache, and why is it eating all our RAM?
To understand that, you have to step back to how an LLM actually generates text in the first place. It's what we call an autoregressive process.
Which is a very fancy way of saying it writes one word at a time.
Technically one token at a time, but yes.
Oh.
It predicts the next token based on everything that came before it.
Mm-hmm.
So if you prompt it with the quick brown fox, it does the math and predicts jumps. But for the next step, to predict the word over, it needs the context of the quick brown fox jumps.
So the input sequence just grows longer and longer with every single new word it generates.
Precisely. And here is the catch. To understand the quick brown fox, the model calculates a bunch of mathematical representations. These are vectors for those specific words.
Okay.
If we didn't cache them, if we didn't save them, the model would have to recalculate the math for the quick brown fox every single time it generated a new word.
That would be incredibly inefficient. That sounds like it's like rereading the first 10 pages of a book every single time you want to read page 11.
That is a perfect analogy. It's
Yeah.
quadratic complexity. It just gets slower and slower the longer the sentence gets. So we cheat.
We cheat.
We cheat. We calculate those vectors once, specifically the key and value vectors, and we store them in the GPU memory. And that is the KV cache.
Okay, so we're training memory for speed. We store the data so we don't have to recompute it. That sounds like pretty standard software engineering. Where does it go wrong?
It goes wrong because of the sheer scale of the data. These vectors are not small. The paper uses the OPT13B model as their benchmark. That's a 13 billion parameter model.
Which by modern standards is actually considered mid-sized, right?
Oh, absolutely. Compared to the massive proprietary models, it's almost lightweight.
Right.
But even so, the KV cache for a single request, let's say a typical conversation that goes on for about 48 tokens, takes up 1.6 gigabytes of memory.
Wait, 1.6 gigs for one user.
For one single user.
So if I have an NVIDIA A100 GPU sitting in a server which has, 40 or 80 gigabytes of memory, I can only handle a few dozen users at once before I literally run out of physical space.
And that's exactly it. You become memory bound. You have plenty of compute power left. The chip itself could do the math faster.
All right.
But you have nowhere to put the scratchpad data.
Wow.
It's like having a Ferrari engine but a fuel tank the size of a thimble. You just cannot keep the thing running at full capacity.
But wait, it gets worse, right? Because the paper argues it isn't just that the data is big, it's that until vLLM came along, we were storing it in pretty much the worst possible way.
Yes. The paper calls out the existing state-of-the-art systems of the time, things like Faster Transformer or Orca.
Hmm.
And those systems use what is called contiguous memory allocation.
Contiguous, meaning all the data from my conversation has to sit directly next to each other in one long line on the memory chip.
Yes. And here is why that is an absolute disaster for LLMs.
Yeah.
Because the system does not know how long your conversation is going to be when you start. It has to guess.
Right.
And to be safe, it usually reserves the maximum possible space.
Ah, I see where this is going. It's like making a reservation at a restaurant.
Exactly like that.
Yeah.
You walk in, and the system says, well, this user might talk for 2048 tokens. So it reserves a massive banquet table that seats 2,000 people.
And then I just ask the bot, what's the weather? And I leave.
Exactly. You use 3 seats. The other 1997 seats are completely empty. But, and this is the real kicker here, nobody else can sit there. That memory is locked.
That is wildly wasteful.
It is. That specific issue is called internal fragmentation. But you also have external fragmentation.
What's the difference?
Well, imagine you have a bunch of these banquet tables, and there are small physical gaps between them on the floor. Maybe enough space for a small 2-person table. But because the system demands a giant contiguous block for every new request, you can't use those little gaps.
Oh, got it. It's like trying to park a bus on a street filled with motorcycles. There's plenty of total space available, but there's no single open spot big enough for the bus.
You got it. And the researchers actually measured this waste. In existing systems, they found that 60 to 80% of the memory allocated for the KV cache was just empty.
Wait, pause on that for a second. 60 to 80%.
Gone. Completely wasted.
That is a staggering inefficiency. I mean, if a manufacturing plant threw away 80% of its raw materials, they would be bankrupt in a week.
And yet, that has been the standard for serving large language models. We were effectively only using 20 to 40% of the GPU's memory capacity for actual data. The rest was just air.
Okay, so the villain is clearly identified. We have huge data, and we're managing it with a rigid system that demands contiguous blocks, which leads to massive waste. Enter the researchers from Berkeley, Stanford, and UCSD. They propose vLLM. What did they see that everyone else missed?
They saw a parallel to computer history. They looked at this exact problem, programs needing more memory than what's physically available, combined with massive fragmentation issues. And they realized, hey, operating systems actually solved this back in the 1960s.
This is the virtual memory concept.
Right. Back in the day, computers had tiny amounts of RAM. If you forced a program to live in one solid contiguous block, you would run out of space constantly. So computer scientists invented paging.
Break down paging for us. How does it differ from the giant banquet table approach?
Instead of giving the program one big contiguous plot of land, you chop the data up into small fixed-size chunks. These are called pages. And you can scatter these pages anywhere in the physical memory.
So instead of needing a banquet hall, I can seat my party at 100 little 2-top tables scattered all over the entire restaurant.
Exactly. And the program, or in our case, the LLM, doesn't even need to know they're scattered. The system keeps a block table, which is essentially just a directory.
Okay.
It says, okay, the first part of the sentence is over at table 4. The second part is at table 12. The third part is at table 9.
So logically, to the model, it looks like one continuous sentence. But physically, on the chip, it's all over the place.
That is the magic of PagedAttention. They divide the KV cache into blocks. In their specific implementation, each block holds the key and value vectors for, say, 16 tokens at a time.
Just 16 tokens. That's pretty granular.
It is very granular, and it solves the reservation problem instantly. When you start a request, the system does not reserve 2,000 slots. It just gives you one single block.
Wow.
As you type more, or as the model generates more text, if you fill up that block, it just grabs another free one from anywhere in memory and links it up.
So it's purely a pay-as-you-go model.
Pay as you go. No massive pre-allocations.
That must eliminate the internal fragmentation, those empty seats at the banquet table, almost entirely then.
Almost entirely. You might have a tiny bit of empty space in the very last block of your sentence if you don't fill it up perfectly to a multiple of 16. But the paper notes this brings memory waste down to under 4%.
Going from 80% waste down to 4% waste is, well, in software engineering, that's usually impossible. That is a generational leap.
It really is. And the impact on performance is direct and immediate. Because you aren't wasting space, you can fit way more active conversations into the GPU memory at the exact same time. They call this the batch size.
Right, and the bigger the batch, the better your throughput.
Exactly. The paper claims vLLM improves serving throughput by 2 to 4 times compared to systems like Orca or Faster Transformer.
Just think about the economics of that for a second. You're an AI startup. You are renting H100s or A100s from Amazon or Azure. Those are incredibly expensive. We're talking thousands of dollars a month per chip. Suddenly, you install this open source software library, and your existing hardware can handle double or triple the
It
customers
cuts your compute bill in half, basically overnight.
without changing the model weights at all, without losing a drop of accuracy. It's pure system optimization.
That's the beauty of it.
Now, I want to pivot to something else the paper mentions because I found this fascinating. We've talked about saving space, but breaking memory into these little blocks actually unlocks some new capabilities, some real superpowers that just weren't possible when everything was locked in giant chunks. They talk a lot about memory sharing.
Yes, this is arguably the coolest part of vLLM.
Mm-hmm.
Once you have this block table, this directory that points to where the scattered data is stored, you can start doing very clever things with the pointers. You can literally have different requests pointing to the exact same physical memory blocks.
Why would different users or even different requests want to look at the exact same memory?
Think about parallel sampling. Let's say you're building a creative writing assistant for a user. The user prompts the bot with, "Write a haiku about Rust." But you want to give them 3 different options to choose from.
Okay, so one input prompt, 3 different output streams.
In the old contiguous world, the system would have to copy the KV cache for your prompt. Write a haiku about Rust, 3 separate times, 1 full copy for each output stream.
Because they all need their own dedicated scratch pads to work from.
Right. But with vLLM, all 3 output sequences can just point to the exact same physical blocks that store the prompt. They share the memory for the input.
But wait, eventually the outputs diverge, right?
Right.
One haiku starts with orange flakes, the other starts with iron bones. If they are sharing the exact same memory block, won't one sequence writing to it overwrite the other sequence's data?
That is where they borrow another classic operating system trick. It's called copy on write.
I remember this from Linux kernels.
Same exact principle. The system is fundamentally lazy. It lets everyone share the block as long as they're just reading from it. But the instant one of the sequences tries to modify the block, to write a new token that is unique to its specific path, the system shouts, "Tause."
Huh.
It makes a copy of just that specific block for that specific sequence and lets it write to the fresh copy.
So it only uses extra memory the exact second it becomes absolutely necessary to do so.
Exactly. And this is a massive deal for complex decoding algorithms like beam search.
Beam search involves the model exploring multiple future paths simultaneously to find the best possible sentence, right?
Mm-hmm.
Like a computer looking 5 different chess moves ahead.
Yes. And those paths share a ton of history. The cat sat on the could branch into mat or hat or floor, but they all share the cat sat on the floor. With vLLM, the paper shows they can reduce memory usage in beam search by 55%.
That is huge. But there's another scenario the paper mentions that I think is even more relevant for developers who are building commercial apps today. Shared prefixes or system prompts.
Oh, absolutely. This is the standard architecture for almost every AI application right now. You have a system prompt a set of hidden instructions that the end user never actually sees. It says something like, "You are a helpful banking assistant. Be polite. Never give financial advice. Output your responses in JSON format."
And that giant prompt gets tacked onto the front of every single user's request behind the scenes.
Right. If you have 1,000 users talking to your banking bot simultaneously, you normally have to store that system prompt 1,000 times in the cache. It's totally redundant data.
But with vLLM's block mapping,
You store the system prompt exactly once in physical memory, and you just map every new user's block table to point to those existing blocks for the first part of their request.
so the memory cost of that long, complex system instruction becomes essentially 0 after the very first user logs on.
It makes complex, detailed system prompts virtually free in terms of memory. That enables much more sophisticated app behavior without bogging down the server hardware.
It really highlights how much we were just brute forcing these models before. It's like we were building a separate, fully stocked library for every single person who wanted to read a book, instead of just building one public library and letting everyone check the books out.
That's a really fair analogy. It's the maturation of the technology. We're moving from, can we do this at all, to how can we do this efficiently at scale?
But I do have to play devil's advocate here for a minute. Even with page attention, even with clever sharing and zero waste, physical memory is finite.
True.
If I keep spamming the server, or if the conversations get insanely long, like passing an entire novel into the prompt, eventually the GPU memory will fill up 100% full.
It will. There is always a hard physical limit.
So what happens then? Does vLLM just crash? Does it drop the user's request?
No, and this is another area where the operating system inspiration really shines. When memory is full, vLLM has to evict something to make room for the active, urgent request.
Okay.
It has a scheduling policy. It effectively puts a less active conversation on pause.
And where does that pause data go? It can't just vanish.
They give it two options. First is swapping. It literally moves the data blocks from the super fast GPU memory over to the slower CPU memory, the regular system RAM.
Like swapping to a hard disk on an overloaded PC?
Exactly like that. It offloads the blocked conversation to the CPU, processes the urgent stuff on the GPU, and when space finally clears up, it swaps the data back in and seamlessly resumes the paused conversation.
That makes a lot of sense. But the paper mentions a second strategy that genuinely surprised me: recomputation.
Yes, this is somewhat counterintuitive. Sometimes it is actually faster to just delete the data entirely and recalculate it from scratch later.
How can doing the massive matrix math twice be faster than just moving a file?
It's all about bandwidth bottlenecks. The connection between the GPU and the PCI bus, is a bottleneck. It is incredibly slow compared to the blazing speed of the GPU's internal processors.
No, I see.
If the prompt is relatively short or the blocks are small enough, the physical time it takes to transfer the data out across that bus and back in might actually be longer than the time it takes the GPU to just run the math numbers again.
That is fascinating. It really shows how speed in computing is entirely relative. Sometimes the data bus is the slow part, sometimes the processor is the slow part.
Exactly. So vLLM is smart enough to leverage that dynamic. It gives the system flexibility. It ensures that the server never crashes due to an out-of-memory error. It just gracefully slows down or queues things up, handling the traffic jams intelligently.
So putting it all together, we've got PagedAttention completely solving the fragmentation issue. We've got memory sharing for parallel task and system prompts. We've got swapping and recomputation for overload protection. And the end result is a 2 to 4x speedup.
On the exact same hardware.
It seems like an absolute no-brainer. Is this becoming the standard now? I know this paper is viewed as a bit of a landmark.
It really is. vLLM has been rapidly adopted across the industry. If you look at the open source community or even the massive big tech hosting providers, almost everyone is integrating these paging techniques. It's quickly becoming the default way to serve LLMs because, frankly, you simply cannot afford to leave 60% of your GPU memory on the table anymore. The margins are too tight.
It definitely makes you wonder what is next for this space. We're seeing context windows, the amount of text a model can remember at once getting larger and larger. Claude is up to 200K tokens, Gemini is even bigger. People are literally feeding entire corporate code bases or massive legal libraries into a single prompt.
And that means memory is only going to get tighter. As the context window grows, the KV cache grows linearly right alongside it.
Okay.
If you want to process a 500-page book, your cache is going to be massive. The pressure on memory management is only going to increase from here.
And we haven't even touched on the shift to multimodal models.
Right. When the token isn't just a simple text word, but a patch of a high-resolution video or a complex segment of audio, the memory footprint absolutely explodes. The KV cache for a real-time video generation model will be astronomical compared to what we currently have for text.
That is a slightly scary thought for the server bills, but also, based on today's deep dive, it sounds like a solvable engineering problem.
It validates a core truth in computer science that I love. The fundamentals just don't expire. We like to think modern AI is this brand new, almost alien technology. But under the hood, it is still data, it is still bits, and it is still fundamental memory management.
The problems of the 1960s mainframes are the exact same problems of the 2026 H100 clusters. We just have way more parameters now.
Exactly.
So here is a final thought to leave you with. If a 1960s idea like paging unlocked the bottleneck for modern text AI, what other ancient computer science concepts are just sitting there gathering dust in a university textbook somewhere? What other completely solved problems from the 70s or 80s, maybe in database theory or network routing, are just waiting to be rediscovered to solve the next big roadblock in AGI or robotics?
That really is the trillion-dollar question right now. Maybe the answer to the next big AI breakthrough isn't hiding in a new research paper, but in a dusty manual for a Commodore 64.
I absolutely love that idea. We'll leave it there. Thanks for unpacking vLLM with us.
My pleasure.
And thanks to you for listening. Keep digging, keep questioning the stack, and we will catch you on the next deep dive.